atomic structure of metals, or in the image, or when you model the game of Go, it's hard to tell which variable is influencing which variable in a unidirectional way, right? You want to have asymmetric dependencies between a pair of random variables. But here you also have some maybe more scientific reasons, even in domains where you believe the influence are directional. For example, when people talk about gene networks or regulatory networks, we often thought about, well, of course, it is a regulatory cascade. Therefore, influence should be sent from one way to the other rather than the opposite. But the truth is that even in those domains, you may still want an undirected graph model representation, just because you may not have enough information to carry or to capture the directionality. For example, in this domain, suppose that we know two genes, A and C, are under the regulation of something called a transcription factor B, in this manner. But in reality, what you really observed might be only A and C, because they are the product of gene activity that is generated in your experiment. The actual regulator, B, might be in a different form, such as a protein concentration, which you cannot measure. And when they cannot be measured, you actually will see, a correlation between these two genes if they are under the same regulation of B, which is unidirectional. Therefore, you probably prefer to use this kind of representation to capture the dependency between these two genes when B is missing, right? And this kind of relationship can be quite important and interesting. And so today we're going to start by studying a particular technique for you to learn simple indirect graph models in this particular context. Again, as I mentioned last time, learning structures from real data is a pretty daunting task if you allow the structure to be arbitrary and the model to be arbitrary. So again, we are going to study a special case in which such problems can be turned into a simple operation with a proper statistical guarantee. And I'm not going to talk about fancier algorithms which gives you fancier graphs, but with no theoretical characterization or guarantees. So the setup is like this, right? We're going to have some IID observation of the data vector, x1 to n, meaning n random variables. And we want to learn now a undirected graph, and we assume that all these variables are completely observed. Okay, so that's the setup. You can imagine these nodes like this being the expression of the gene or the like and the unlike kind of sign in a social network and stuff like that. And before I tell you the algorithm, which is surprisingly simple, let me give you some mathematical context of the proper model we're going to introduce to enable such structured learning or network learning. So we're going to study a very simple model, okay, known as the multivariate Gaussian density function, multivariate Gaussian distribution, which you all know about. And there is really nothing mysterious about this distribution, right? You should know that the form of this, is like a exponential family distribution, and the parameters in this case, let's use for the sake of semantic clarity the mean parameterization. At the moment parameterization, we have the mean and the covariance matrix, okay, covariance of the distribution. And without loss of generality, let's make some additional assumption. Let's assume that the data are centered so that the mean will be at 0. And let's introduce another parameterization Q, which is the inverse of the covariance. Okay? So this changed nothing, but just to call the same thing a different name. And then once you put in these two assumptions into the original definition of multivariate Gaussian, you actually will see the distribution look a little bit differently than what you see here, but a little bit more friendly than as you actually see previously as a model that shows a direct connection between the distribution and the graphical structure. So it can be written like this: P of 1 to P xp, P here means the number of random variables, by the way, I think I got already introduced some confusion here. Originally, I set the number of dimension to be n, but in here, let's assume them to be p. N is reserved for the number of data points. Okay, and now they can be written in this form. This is rather easy because mean is 0, and now this guy is not an inverse of a matrix anymore. It is just a matrix itself, Q. And then you just do this dot product between a vector and a matrix and a vector, and you will see these two terms. One is a quadratic term on a particular variable multiplied by the diagonal components in this matrix, and the other is a pairwise component multiplied by a coefficient which actually sits in some locations in this matrix, some off-diagonal locations. Okay, so this is nothing strange. So from here, what do you see? I hope you see that this particular distribution reminds you what we learned before called a Markov random field, in which you have something called a singleton potential and a edge-dependent potential. And the form of the potential functions happen to be defined as a product between the two variable states and the square of a single variable. Okay. So what is the goodness about this form? Well, the goodness about that is that now you can directly form a mapping between this joint distribution, which define the likelihood of data, and actually some kind of structure over the random variables. For example, if you see this Q coefficient to be 0, that pretty much means that this potential function receives 0 weights. And that pretty much means that in the Markov random field, that edge is not present.
How strong are the assumptions that your random variables are distributed according to multivariate Gaussian?
It is a very, very arbitrary assumption. You don't like it, you can take that away, then you lose the power of learning anything. Right? Whenever we want to learn something, we have to make an assumption. For example, we kind of assume that anything is a Gaussian if you have more than 12 random effects into the distribution, into the variable. Here, I don't want to comment on that. I basically want to say that if you are seriously interested about learning some graphical structure, you probably have to limit yourself to this case. Whether the data is really Gaussian or not, I don't know, but this allows you to learn something out of it. Yeah, here, actually, I really want to get into the debate of whether an assumption is reasonable or not. I prefer to stay a step back, saying, if you believe or you want to take this assumption, let's figure out how to make it happen. I'm more worried about the how problem than the why or that kind of deal, because that's mostly philosophical. All right, so this is now a pairwise Markov random field, and you actually can actually see, a interesting statistical interpretation of those pairwise potentials. These kind of structural meaning interpretations are a little bit, less intuitive to a beginning modeler or to a empirical scientist. For example, what is correlation mean, right? Covariance mean. Usually, when you are in a multivariate domain, you probably heard people talking about let's build a graph based on pairwise correlations and stuff like that, right? And that's pretty much equivalent to saying that you want to learn a graph which correspond to the structure of this covariance matrix. So what is the statistical meaning of that? Well, it is better to examine, maybe more easily, what is the meaning of not seeing a element, in the correlation matrix, covariance matrix. For example, here, if this one, has a 0 element, that basically means that these corresponding two variables are absolutely marginally independent of each other, right? And if there is a non-zero element there, that means they are marginally not independent, meaning that they are marginally dependent. Okay, but the implementation of a 0 in the Q matrix is quite different. Without reviewing the semantics of the Markov random field, you probably know that now a absence of a edge between the two random variables means that these two random variables are conditionally independent, right, given the rest of the graph or given their Markov blanket. Therefore, we can write this. They are conditionally independent rather than marginally independent. Therefore, you can now factorize a pair, a marginal of a pair like this. So what is the big deal of that? Okay, the big deal is quite subtle. In fact, it may not be a big deal to many practitioners, but to me, at least, I think it's important. So first, let me ask, when you actually learn a graph, what do you want to get out of the graph? Why do you actually care a graphical expression or representation of the domain? Well, I guess to me, I want to view the graph as an entirety, as a single entity, and therefore, the entire graph should be read as one piece of information to tell the interdependencies or, conditional independencies among all random variables, right? This actually kind of desire, in fact, is only statistics supported in a graph built on precision matrix instead of covariance matrix. Because you can see any dependency statement in the covariance matrix representation is a marginal one, not a conditional one. Meaning that if I see, for example, a graph, okay, which has an edge in here, an edge in here, and if this graph is read off the sigma matrix, this edge actually means that this pair of random variables is marginally correlated if I don't see anybody else, conditionally on nothing. Okay, they don't actually say that they are marginally dependent or independent given the rest of the graph. In a sense, when you see the whole graph, you actually need to read the information out of the graph by pretending that all the other edges or nodes are not present. You have to read them one by one. Okay, but in a graph built on the Q matrix, okay, a edge or a non-edge between a pair of random variables actually means that this is the statistical dependencies of this pair conditioning on everything you see in the rest of the graph. To me, it is more meaningful. Okay, so this graph is also known as a Markov graph. Okay, and that graph is called a correlation graph. So correlation graph should be read single edge by single edge, and a Markov graph can be read, in its entirety. That's the difference that I want to state. Of course, you can choose now which graph you like. I'm not having an opinion, but you need to know what they are doing here. And in particular, in some cases, there are certain dangers actually in applying this. For example, if I use correlation and to study, some dependencies between 5 nodes, in which, one node may be actually governing the other nodes, okay, through some biological processes or some natural processes. And this is a kind of a causal or maybe even a symmetric influences. But if you want to capture this kind of dependency using a covariance matrix, anybody can guess what's happening, what's going to happen, what kind of graph you may get? Yeah, you will be unfortunately getting a graph like this. Okay, it's going to be a fully connected clique because every pair is actually dependent. And if you compute a marginal correlation between every pair, they will all have some kind of dependency. Therefore, you will get this horrible graph. You will find very dense graph as almost like a clique in your direct computation, and you'll fail to get the deeper, semantic meaning out of it. So for that reason, again, I personally prefer a Markov graph. All right, so that's a justification of this business. Now let's talk about why it's a big deal computationally, why we actually need to care about that. Because after all, a Q is an inverse of sigma, right? No big deal. I can just get the sigma as if I'm computing the correlation graph, and then I do an inverse of that. Right? Why it becomes a big deal? Oh, again, here I have another graph, picture helping you to understand the differences between a Markov graph and a correlation graph. So in here, you have this matrix, right? And in fact, if you look at the correlation matrix, there are no zero elements. But if you see the Q matrix, actually correspond to this graphical model. Okay. All right. So why it's a big deal? The big deal is the following. In many domains, especially in the modern applications, we are in this so-called high-dimensional complex world. Sometimes with big data, but let's imagine that in certain domain, the data size may still lag behind your desire to learn complex hypotheses. So in this particular case, let's assume the following scenario. Say you want to estimate a gene network for 10,000 genes, which is pretty typical for a human being. And what you get samples collected from, say, 1,000 individuals. Now, maybe even 100 individuals. That's a big deal, in fact, experimentally, because it's very expensive to collect this information, right? You need to pay everybody a fee, buy the equipment. Probably every sample costs you a few $1,000s, right? So you really don't want to go infinitely big. If that happens, how can you actually get this estimator? Or can you get it at all or not? Any comments? So I can certainly compute a sample covariance, right? And so we know also how to do that, right? It's n equal to 1 to something, and x minus x mean, and so on. So you get that from 100 samples, and then you are going to. By the way, this whole vector is 10,000 elements long. And how can you get the Q matrix? Can you just do this? Can you do that? Right? This is a ill-conditioned matrix, therefore it is not invertible, right? And that's actually the big deal. Such matrix exists, but you cannot get it from this procedure because it's not an invertible matrix.
You can try SVD.
Okay. SVD, how do you go from SD to here?
You can use the low rank. Or you can use the PSA.
Well, I mean, you guys are certainly very smart. You know a lot of keywords and fancy names, SVD, PC, and all that kind of thing. How that connects to the graph? You need to think through that. It doesn't go there. Okay, it does not go there. At least not as far as I know. You get the low rank approximation to the matrix, and then what? Right? I want a graph over the entire set of nodes. I don't want to shed off any subset of nodes that is not, you can use a low rank or low kind of order matrix. That's not fulfilling my goal. Okay. But you can try. I'd be happy to hear any good news if you figure out a different way. This is actually a very hot topic nowadays in statistics, how to estimate this precision matrix from high-dimensional data, for high-dimensional data from limited amount of samples. All right, so let me tell you one idea, which I hope you appreciate. So recall we know how to do lasso experiment, right? Lasso regression is about, basically having a bunch of covariates, and I assume that they make a prediction on some output, right? And then I also assume that not all the covariates are generating a effect. Therefore, each of them should be associated with a coefficient. Then I can use the lasso to obtain a sparse estimation of the theta vector, right? And basically, I can actually get a estimation of the variables or covariables that are influencing this particular output. That's the lasso idea. Okay. It turns out that you can actually try the following idea. Now we have a multivariate distribution following a Gaussian of 0 and Q precision. And I encourage you to go home and do some experiment and figure out what is the conditional distribution of any random variable giving complement of that. Okay, and see how that look like. Without telling you more stories, I will suggest you that this looks like actually a one-dimensional Gaussian distribution whose mean is defined by, that rest of the vector, okay, and multiplied by some q vector, okay, and scale to some other kind of magnitude. And this q vector, what they correspond to? They actually correspond to a column or maybe a row in this Q matrix. Okay, so if I told you that, now, maybe you can already see some funny, interesting connection between estimating this Q matrix entirely to estimating the Q matrix column by column using maybe a slightly different estimator. Maybe just estimating this very simple, one-dimensional Gaussian distribution, for p times, each time for a particular column or row in that Q matrix. Okay, and how do we actually do this parameter estimation? Under this for a Gaussian, and of course there is a noise I didn't write here. So I invite you to go back to the old lecture notes of linear regression and check that linear regression, if you assume a Gaussian noise, after all, correspond to a maximum likelihood estimation of this model. Okay, and a sparse version of that actually correspond to the lasso, because you imagine many of the estimators in this matrix will be 0. And to make even this estimator well-conditioned, you again need to put a sparse regularizer for the number of non-zero coefficients in theta, right? In sigma, sorry, or in theta. So what we are going to do is the following. Now we actually take p, minus, let's say p minus 1. This is p minus 1, and I put this one to be xp. Okay, then I basically do a regression of all but one random variables in my domain to that remaining vector, remaining random variable, through lasso. And then I'm going to solve the lasso regression problem and get maybe some of the random variables on this side to be selected as the neighbor of this one. Okay, and that's done through a good estimation of this vector, which is now called a theta vector. Okay, so that procedure actually gives you a hint about how we can solve this Q matrix problem, progressively. Okay, so here is the bigger picture. We start by this graphic, this set of random variable, empty, meaning that we only have data, no structure, and we're going to pick one node at a time and perform a regression from the rest of the random variables to this one using this lasso regression. And we're going to keep those non-zero coefficients, okay, so that they indicates the neighborhood of this node in the graphical model. By the way, here I only care about the fact that edge being 0 or non-zero. I didn't really say I care too much about the theta magnitude here, other than the fact they are 0 or not. Why? Because this solution is not quite the same as this solution yet. They only have correspondence in terms of 0 and non-zero. They are not necessarily the same in terms of the actually value of that. Okay, so I'm going to do this, and then after this is done, I'm going to pick another node, okay, and do neighborhood selection again through lasso. And you can imagine I just go through every node, and if edge is estimated from here to here, but not here to there, I'm going to take a union of that, just to count edge if they occur in at least one of the direction. And at the end of the day, I get a graph. Isn't that amazing? This is a very, very simple algorithm. Lasso, already. And now it gives you a sparse estimation of the structure of a Markov random field, or of a continuous Markov random field, also known as the Gaussian graphical model. Okay. That's also why the multivariate Gaussian distribution is also known as a Gaussian graphical model, because in the really useful multivariate Gaussian distribution, you actually have a graphical model corresponding to that, which is a sparse kind of estimator of the dependency structure. Yes?
So how do you control the lambda? It seems that you can get whatever you want.
No.
Use that.
That's not true. Okay. The lambda actually can theoretically be analyzed to favor a particular setup. And if you study the literature of the lasso, you actually will see that there is one true lambda which can be found actually through something called a regression path. You can basically vary the lambda, okay, and from small to big. And here are the coefficients of, all the regression coefficients. And at some point, they will all quickly drop to 0. Not all, but the one which correspond to the 0 weights will actually drop quicker than those which are not belong to 0. The one which are truly non-zero will actually have a kind of a smooth kind of a degradation to the small value, and you spot that phase transition. Of course, here in practice, you can use the lambda to control the density of the graph, but you can see it is a very easy control. It's almost like microscope now. You just tune the number, and you can start to see the whole graphical structure, which is kind of cool, right? That's how people practically practice. If you really want to have a true lambda, one other thing you can do is what? Actually, you should know better than I do now. We talked about multiple times about variable selections or variable tuning through a kind of a principled approach, which is what? Which is cross-validation, right? You kind of set out a data set, and you get the lambda to be that producing some result you want, and then you come back to the original problem you solve. Okay.
So in this case, what is cross-validation?
You can cross-validate by their predictive accuracy, because you are predicting every node from the rest of the node. That's one setup, right? And if you have some ground truth graph on certain variables, for example, an edge must be present between a particular pair. This is a creative business that I want you guys to be creative. I can tell you a few ideas, but I bet there are more ideas than I can tell. Right? All right. Again, I'm going to revisit this domain later, and this whole kind of a statistical background is covered more intensively in 702, where the proof of the correctness of this technique are carefully studied in detail. And here I just want to wrap up by one thing, which is that that procedure has a very nice statistical guarantee under certain assumptions. Again, that assumption is something I may have time to revisit next time, which really depends on how good the data is. Okay, and if you look at the original lasso paper or the graphical lasso or graphical regression paper, there are keywords such as e-representativeness, okay, and diameters of the data, stuff like that. If we have time, we may go there. But here, I want you guys to take home the algorithmic kind of ideas that I just talked about. So the nice thing is that if your data is truly generated by a graphical model with a known structure, and then you present the data to the algorithm, the good news is that the algorithm is likely to recover that structure if you keep increasing the size of the data. So this is a kind of a consistency many statisticians would like to see or to have for any algorithm. And that's actually, again, a new tradition now in machine learning. If you look at the textbooks 10 or 15 years ago, we learn algorithms, KNN, decision tree, without worry about what they produce eventually. But nowadays, any good machine learning algorithm is expected to have this kind of guarantee so that they can be theoretically characterized. So let me ask you one more question before I wrap up on this part. What if I have a discrete Markov random field, an Ising model? So they symbolically look the same, okay, except that now the x are binary or discrete variables. And you have now also an annoying partition function A here, which prevents you writing the whole likelihood in closed form, or the conditional probability of a node given the other nodes in a closed form. So what do you do? Do you want to make a good guess? Oh, I thought I had a solution here already. So the natural thing to do is that linear regression is about predicting from neighbors the continuous value of that remaining node. And in the discrete case, I can imagine predicting the value of that node from the neighbor, although the prediction is going to be discrete. And we know how to make discrete predictions, right? It is going to be done through a logistic regression. So in here, you're going to basically form a conditional distribution in using a logistic, and this is a approximation to the actual maximization of the likelihood, the data likelihood under this model. This is something called a pseudo likelihood estimator. Okay, but again, the gist of this idea is that you may get wrong in estimating the value of the theta, but you cannot go wrong if you only care about the zero and non-zeroness of the estimator, because that's what you need in defining a graph. Okay, and if you really care about the value of the theta, do you know what you do? This is an open question. I fortunately didn't write here, so you need to now try your guess. So through neighborhood selection using either linear regression or logistic regression, you now have the guarantee to get a graph correct. How can you get additional guarantee on value consistency? This is called sparsistency or graph consistency. And this tool, if we want to have a good estimator, is called value consistency. How can you get that? So now let's be creative. Try your best guess. Yeah.
Once you have the support, you can, since you have a lot fewer parameters, you can probably use like the MOE estimate on just that support.
Good point. That's great. So yeah, you need to now divide the whole thing into two steps. You run this algorithm to get the graph estimation first. And then once you have the graph now consistently, hopefully, estimated, you are now in the regime of estimating parameters with known graph structure. Okay, and that's the stuff we're going to talk about now. Okay, you have some other algorithms to estimate the known, the structure, the parameters of the known structure. All right. So let's study a few algorithms for that purpose. In fact, this is a pretty dense part in the lecture. I'm not sure I can finish the whole thing, but let's try. There are a number of different scenarios which make this type of estimator much more complicated than what you encountered in Bayesian network. All right. So we're going to observe the structure, and what do we mean by estimating the coefficients or the parameters? Well, in the Bayesian network or the directed graphic model case, we know very well, right? It's about putting numbers in these little tables, two-dimensional table, three-dimensional table. They are basically local conditional probabilities of children's given parents, right? And we know how to do that. And the one key effect, if you can remember, that we use to make this estimation problem easier is this decomposition property, right? We put a log, on this data likelihood, then everything decomposes, and then I can basically estimate every of this little table independently from the data, right? And that actually makes the problem a lot easier. What makes a undirected graphical model much harder is because we now don't have this luxury of decomposability, okay? Which can be seen from here. So now the joint likelihood of the data is defined by a product of not conditional distribution, but cliques or potential functions on the cliques, right? And then they will be, again, multiplied by something called a partition function, okay? And this partition function is computed using this equation. And by definition, it is a function of all the parameters you have to estimate in the graphical model. Okay, so this whole thing, this little thing, is a function of all the parameters, okay, in the model. And that's why it is impossible to actually decouple the learning of the parameters into separate pieces, because this one ties together everything. Okay. All right. So now what should we do? First of all, let's understand the following. What do we mean by estimating, the coefficients here? It looks like we want to estimate the potential functions, and in the simplest case, a potential function is basically of variable states. Right? So there's 0, 0, and you put a number here, and the 1, 1, you put a little number here. And that's basically what I meant by estimation. So therefore, this function actually corresponds to some unknown numbers or unknown coefficients. And in here, the numbers doesn't have to be probabilistic. They don't have to norm to 1 or smaller than 1. That part is making your life a little bit easier, but the fact of coupling of all the variables is making your life really hard. So now let's take a look of what we are going to deal with and see, how can we begin this endeavor. Okay. First, let me introduce some tricks, okay, some conventions to make a notation and manipulation of the likelihood function a little bit easier. I'm going to introduce something called a counting function, okay, M. This basically corresponds to the number of instances you see in the data, which takes a configuration x, lowercase x. Remember, we use the uppercase x to be the name of the random variable, and we use the lowercase to be the realization of the variable in its value space. And here it is bold-faced, meaning it is a vector of such random variables. Okay, so this is a counting of this configuration, and this is another counting of the configurations in that clique C. And this can be related to the global counting by something called, something similar to a marginalization procedure. You just sum over all the other variables not in the clique. Okay. So with that, let's see how can we, manipulate this joint likelihood. Okay. So the joint likelihood used to be written in this, right? We basically say it is going to be multiplied over n pieces of the data, and then each one is now, n given the theta, something like that. Okay. So I'm going to rewrite this a little bit, okay, to actually introduce placeholders of all possible values, okay, in your parameter, in your data domain, in your data space, so that our estimator of the coefficients can be, applied to all kind of data configuration. So this is the trick. Instead of using this form, I'm going to now use an indicator function delta, and then I'm going to multiply this over all data configurations. Okay, so on every data point, here I multiply n times. Therefore, the inner term is a particular data point, and it can take arbitrary, configuration of the x value. One of them will be true, which is equal to what I actually observed. Okay, so I basically rewrite that to this one. And I put a logarithm here, and I got this reformulation. And why it's interesting? Well, here I'm going to change the summation sign a little bit to bring x outside of n, and then I can start applying the so-called counting operation. Okay, here I'm summing over, not over data points, I'm summing over all the configurations you can encounter in your data, and then the number of times they actually occurred. And therefore, now I have a different form of the log likelihood, which is over all possible configurations, the number of times such configuration occurred, and over this. This is the definition of the Markov random field. Okay? And here, I made explicit that these potential functions is defined over clique and over a particular configuration of the clique, and you are going to enumerate all configurations. Clear about that? Now, what is the thing we want to learn? Okay, we want to basically learn this guy, right? And this guy is what? This guy is basically a table of some numbers, right? The number corresponds to each of the possible configurations enumerated here. So what should we do? Well, to learn these coefficients, which are maximizing the log likelihood, we do, we compute a gradient of that with respect to that, and that's happening here. There are two terms, okay, and we deal with them one by one. The first one is very easy. It is a linear form, actually a logarithm of the coefficients, and taking derivative over psi gets you, m over psi, okay, of that clique configuration. You should know that very well, right? And the second one is a little bit trickier. We need to now learn how to derive a gradient over the log partition function, which I put up in here. Again, here I used a few tricks to rearrange the term a little bit. So in here, I have this is the definition of the partition function, if you can still recognize. Okay, by definition, z equals to the product of all clique functions, sum over all configurations. Here I introduce x tilde just to make sure that this summation is happening without the interference of anything outside. I just want to avoid configuration of the enumeration of configurations. And then this guy is going to be taken derivative over this guy, which is a particular configuration of the clique. That means many of the configurations here wouldn't actually affect the final value of the derivative, right? Therefore, many of the terms will be eliminated. And therefore, we introduce a operation. We use this delta, again, to set up an indicator. If what you enumerated over is equal to the configuration in here, we keep it. Otherwise, we zero it, right? So by that, we can now move the summation sign outside. Okay, and then you now can do derivative with respect to potential of C over configuration C with respect to this, and then you are going to get what? Well, in fact, the trick here is that so that will give you actually this term, okay, which you can actually figure out by yourself why this actually corresponds to that. Okay, it is very easy. You can introduce a z and cancel that z, in the next term by introducing some additional terms. Okay. Anybody want me to explain that step, or you'd rather go figure out by yourself? Okay. Derivative removes one of the terms equal to c here, and you bring them back here, and you multiply downstairs, which gives you this, and then you have the z recovered on upstairs or on downstairs. All right. After all this arrangement, at the end of the day, you get something like this, which is a nice, clean, simple term, right? The derivative of the second term with respect to the coefficients, or with respect to the potential function, is taking that simple form. All right, so all nice and clean, and let's put things together. We have the derivative of the log likelihood with respect to the potential function equals to, these two terms. All right, now how do you solve that? We can solve it like this. We put them to 0, right? And then, a natural thing to do is, in algebra, we all know how to do that. For any terms which appeared on the left-hand side and right-hand side of the equation, we should cancel that. Okay? All right, so now we have a super clean kind of equation, which is m of xc equals to n of p xc. Okay, now we finished our derivation, which is very comforting, except that now we lost the very thing we want to solve. We want to solve psi of xc, but in our final derivation, that term vanishes. Right, so
xc, when you cancel out, you're assuming that the potential function is non-zero.
Oh yeah. And let's of course ignore that kind of little technicality. I assume they are not zero. After all, we care about non-zero potentials, right? Yeah. Anyway, we can make some exceptions, to enforce that law. But this seems to be the general outcome. If you do the naive cancellation, you actually get something like this. Okay, so you are not quite there getting an estimate of that, but you get some interesting kind of equivalence. By rearranging this a little bit, you actually now get what is known as the empirical estimation of the clique marginal, okay, obtained by dividing the counts of that marginal over the entire counts, and this one equals to the actual kind of marginal probability defined under the distribution, which is not surprising, right? The actual marginal equals to the sample marginal or the empirical marginal. All right, so what shall we do? We are kind of at the end of the road and lost our target, right? And so this doesn't really tell us how to estimate the parameters. That's basically what I meant to say. Well, although in some cases you may be able to get a reasonable estimator if you are willing to assume that this guy is somehow directly related to this guy. If that happens, you may be able to make use of these counts. Okay, so let's first examine this type of scenario, and then we're going to move forward and deal with the case where such a equivalence is not necessarily there. Actually, now it's a good time to remind you or to ask you, do you still recall any cases we can have this kind of equivalence between a clique potential and a clique marginal? I kind of mentioned that very briefly in one of our previous lectures on a particular type of graphical model or Markov random field. Still remember? All right. So if you remember, at some point we talked about certain graphical models being decomposable or be triangulated or be having a running intersection property. Remember that? And we said that if a graphical model had that kind of a nice property, of course, one function or one utility is that you can do message passing on that graph without worry about having cyclic or having non-convergent results. But the other thing which we kind of played on is that we can express the joint distribution of everything in that kind of graphical model by using a strange kind of definition of the potential functions, which basically is p of phi of kind of clique potentials, phi potential function of the cliques over potential functions of the separators. Remember that, right? So that basically gives you some hint about maybe treating these type of potential functions a little bit differently if the potential functions are defined on triangulated or decomposable graphs. Because their definition comes to this form, then there is a potential for you to establish a one-to-one correspondence between the potential functions versus the marginals of the cliques. Okay, this is just by pure inspection. You really don't do any derivation, but by inspecting that, for example, I have a graphical model of 3 nodes, which is of course a decomposable graph, and then you can kind of write down the potential as P x1, x2, x3 equals to these two potential, x1, x2, and x2, x3, and divided by x1, right? Now, you can also write this distribution as this term, okay, which kind of looks similar to what you have here. And then one way of making the connection is that why don't you just define the potential functions using the marginal, the clique marginals, okay? And in this case, your clique marginal can be directly obtained from the counts that we obtained. Okay. All right, so this is kind of a weird case that you can build this nice connection between clique potential and the clique marginal. And I have a few other cases where you can, for example, in this case, you have this bigger kind of clique potential on 3 nodes, but still you can relate one of the cliques to be a conditional, the other to be a marginal, and then they all correspond to empirical counts that give rise to the empirical marginals or conditionals on certain random variables. So what I'm trying to say here is that even if you have kind of this useless relationship, seemingly useless relationship from the early derivation, you can still use this rule to estimate phi of xc if the phi of xc is defined on certain graphic model or decomposable graph, which makes them corresponding to the marginal potentials or marginal distributions of the clique. Okay, and this derivation or this result happens by inspecting the graphical model, which obviously is not very elegant. For example, you can have some counterexamples. In here, I have a graphical model which we know to be non-decomposable. Suppose if we define the potential only on the edges. And you can actually show to yourself that you cannot actually define the potential functions to be either a clique, either a pairwise marginal or a singleton marginal. Okay, so that idea is not going to work here. All right, so now what we do? We are in the space of more general kind of potential functions, okay, on non-decomposable graph. And we actually will be running into even more difficult case later on where the potential function itself contain additional parameters. So here I'm showing you a roadmap of some more fancy technology in estimating this. So let me first make sure that you are still with me. We already visited the case where in here the clique potential directly connects to clique marginal. Okay, that's our first case. We know how to do that already. And our second case is a more general kind of clique potential, which is just a table, for example, x1, x2, and pi, and then you put basically 10, 1, 0, 0, 1, 0, and so on. Here you have some numbers. These are arbitrary numbers, okay, but they don't actually directly correspond to the clique marginal. We need to know how to figure out those numbers. And then I have a third case in which these potential functions is not just a tabular form. They can be itself a function with its own parameter. Okay, then that invokes a third type of problem which needs a new algorithm. So here I give you some guideline. The first one we know how to do that already. The second one we will be discussing an algorithm called the iterative proportional fitting, IPF, and then we're going to study this algorithm using a algorithm called the general iterative scaling. Okay, let's see how far we can go from here. Okay, everybody still with me so far? All right. All right, so here is where we landed previously, right? And we knew that after canceling these two, we pretty much get stuck, in doing anything with the potential function. So the idea is to keep it in some way. So how to keep it? Let's try this idea. Maybe we should really, redo some of the manipulation, or take a more out-of-box thinking by observing the following. So here we have counts of the clique, and it is divided. Actually, let's move the n to here. Okay, from this square to here, and I keep the other term, which is the clique potential. Okay, and then what's left there will be P of xc, which is the clique marginal, divided by, again, the clique potential. All right. And then I'm going to do the following. Maybe, this guy, we know what it corresponds to, right? This is the empirical marginal on the clique, right? So we're going to call it P tilde over xc divided by, again, the clique potential. And on the other side, I have the true marginal, okay, from the original distribution, which is unknown, by the way. This is something what we don't know, and divided by xc. Okay. So realize that this guy is implicitly a function of potential C, because it is the true distribution which should be using all the clique potentials to define, right? All right, so now we are in here. What shall we do? I propose the following, which I found to be quite interesting. How about let's forget about a closed form solution once for all, and let's revisit the idea about fixed point iteration. So anybody heard about fixed point iteration, right? The simple operation is that you have the same quantity or variable on both sides of the equation. You set one side to be the older version, the other side to be the newer version, and then you make these temporal dependencies between the older version and the newer version, right? So that's what we're going to do. Let's, I'm going to use another color. Maybe we should try call this a t+1 version, okay? And let's call this a t version. And then these two things would not cancel anymore because they are actually different, right? And okay. And then the fact that here we also have an implicit function which also actually contain the estimate, or the one we want to estimate, we can basically put maybe also a t in here, right? Okay, so that's basically giving you this kind of iteration, okay? Actually this kind of iteration. We're going to rearrange the whole thing a little bit to move everything, indexed by t to the right-hand side, and everything belong to t+1 on this side. Then we have this very interesting iteration, okay? So how can we kickstart this process? What is phi t0 correspond to? Well, we've been in that situation before, right? For any iterative procedure, we want to kickstart by a random guess, right? So you kind of get a random guess here, and then you keep iterating. And that basically gives you an estimate of the psi if it's converging, okay? Then, of course, what you need to do is to prove that the loss function is a convex one and maybe a smooth one. Then using this iterative fixed point iteration, you are likely to guarantee to converge to a global optimum point, right? And you should know that we are dealing with a exponential family distribution, and when data are all fully observed, the loss function is indeed a convex one versus the parameters. Therefore, this one will get you to a global convergence. Okay, so that's all good news. And that's basically our so-called IPF algorithm, iterative proportional fitting. Why that name? It's because now you are going to start with a random guess of that clique potential, and they're going to kind of recalibrate, okay, iteratively by the proportion of your empirical marginal over the true marginal, resulting from the last round of estimation of the potential functions, right? And hopefully this ratio will be changing slower and slower once you iterate more, and then they will cause a convergence.
So here the P iterative will not change, right?
The P what?
P iterative, the P iterative.
Oh, this one?
Yeah, actually, this one. It will not change.
Yeah, they will not.
And the PT.
This one will change. Yes.
And according to the reading materials, it says that the B t plus 1 equals to this term, the first term. So this term will be, from the reading materials, I think all the PT here should be equal to the first one.
This one?
No, P tilde.
P tilde?
Yeah.
Oh, yes.
According to the reading materials, the P t plus 1.
This, you mean this one should equal this one?
No, PT plus 1. That's
PT plus 1.
the probability of xc at time t plus 1 should be equal to p term. But it sounds like all the pt should equal to that term, but that term doesn't change. And then
remember here, I'm not talking about a estimation. This actually is you're asking a very interesting question. How do we get this one?
Yeah,
okay, right.
Yeah.
This one, if we get them from data, by our earlier definition of, P, then it is cyclic, right? You don't use that. Actually, this one is the analytical marginal of that clique, resulting from your current estimation of the model. In fact, I want to appreciate your question because you remind me something I forgot to mention. Why actually learning undirected graphical model is difficult? It is difficult exactly from this step, because to compute a P of xc analytically, okay, at least the true estimation, needs you to do a marginalization of x minus c over the entire distribution. And that entire distribution was what? Was basically, composed from our current collection of all estimated potentials. Therefore, this equation suggests you that when you do learning of Markov random fields, you actually need to do inference at the same time, even though everything is observed. Okay, here we have a fully observed domain. As you said, we actually observed this already, but we cannot use it. We actually need to estimate the marginal distribution of this clique under the original distribution, which actually is a very interesting inference problem. Okay, get that point, everybody? Okay, learning contains a non-trivial inference step. And that's why even for learning fully observed Markov random field, you need to call a routine for very complicated inference, in certain cases if your graphic model is quite complicated. There are some other notions called I projection in here. I think we are running a little bit of time. I'm not going to discuss that to a great deal, but you actually can see some additional slides at the end of the lecture to understand more about this. Basically, what we are doing here is like a projection step. At every point, you are holding one, clique potential fixed, okay, so that their marginal distribution is also fixed, and then project the others to a surface where you have all the space of parameterization, but the one that is the biggest is maximizing the entropy, which is equivalent to maximizing the likelihood. And so this kind of connection is discussed in detail in Jordan's book, so I'm going to skip that part. Okay, get the message. A algorithm based on fixed point, and then an inner step which require non-trivial inference procedure. All right, I have a couple of slides actually justifying this statement. which I choose to pass. And now let's actually move on to a even more kind of generic but very useful scenario in which we need to deal with potentials like this. Okay. So why we actually care about potentials like this? Anybody want to comment? The reason is because these type of potentials, although very convenient to define, can be very expensive. Okay, so here I have an example. Suppose that you want to say set a potential function for characters in English word, and you just want to maybe set up a potential for a sequence of 3 characters, or even 2 maybe, but 3 is a typical example. Then that means you need to set up this gigantic table of how many components? 26 to the power of 3. And by definition, the potential function need to have values for each of that. Okay, and again, they shouldn't be 0 because a 0 potential causes the whole thing to collapse, right? So we actually want to insist on non-zero potentials. Okay, and the consequence can be rather annoying because you need to now do this inference problem in a huge kind of space, and getting all the entries in this table kind of filled in with empirical estimations and also with inference on the true marginal potentials, clique marginals. Right. So people don't like this idea. In fact, people find it unnecessary to even have that kind of setup. For example, in the English character, you don't really need to put a potential for all possible triplet of characters. And also, there are many triplet of characters which may be roughly equally, weighted, in terms of their probabilistic strengths. And so, you want to focus your effort on those really useful ones. For example, these kind of triplets are quite interesting, and I expect it. But the triplets of X, Y, Z really does not deserve anything, right? And also, there could be sometimes a wild card, such as a question ED and QU something and so on, and they probably need to be lumped together, with a common parameterization, right? So that kind of needs, somehow inspired a new type of so-called feature-based potential function, which basically we're going to just single out those things, those configurations we actually care, and put them a feature, okay? And then we're going to collect all these features in a linear additive way, okay, weighted by their strengths, and then use that to define this potential function, right? So this is a 3-state potential. In principle, if you use a tabular form, you need 26 cube number of parameters. But in this case, you really do not need many parameters. Well, you need as many as you want to model. Okay, so for each of the triplets on the doublets and stuff like that, you are going to put a feature, and you can put all the rest that you don't care to be an intrinsic feature and give them an overall weight. Right? So that gives you, this particular form of the potential function. Okay. So that's certainly saving you a parameterization cost, because now you only need to care about this. And that F is by design. You can actually influence the design by yourself, making this ing to be score 10 and that one to be score 5 and so on. All right, so having that, now the question is that how can we learn the theta from data? Okay. It turns out that presence of the theta creates some additional questions. Okay, because the equation we learned before, in here, is really for iterative proportional fitting of the entire configurations of the score of the entire configuration, okay, in that potential, in that clique potential. And it is not quite clear how to actually use this same trick to actually re-estimate the theta, which is the weight in this inside this potential function. Okay, And you can actually try some trivial derivation by yourself and find that this procedure isn't really working very nicely. Okay. So now what should we do? Well, we are going to derive a new update equation so that we can use a slightly different update rule than this one to allow us learning the theta. Okay. So this algorithm is known as the GIS, the general iterative scaling, for the feature-based graphic model. And this is a very useful algorithm because that's the kind of graphic model you will encounter most of the time, okay, in your modeling world. All right, so we are going to write down, as before, this log likelihood of the data. Okay, and what is the main difficulties in here? Well, the main difficulty first is this guy, right? This guy is a quite complex function over the free parameters that we are going to estimate. Okay. Originally, it was complex because it is a function of the phi, of the psi. But now the psi is again parameterized by even additional weights, multiplied with the feature score. That makes the whole thing a little bit more complicated. And naturally, what you want to do is to make this as an objective, take a derivative over the theta, and hope to see some nice formula, right? Maybe a gradient or something. But let's try see what's going to happen. Well, first, taking derivative against this guy is not that easy because you basically will be keeping this one in the denominator, and nothing will actually change. Okay, computing you still need to compute the partition function even after you actually compute the derivative, right? And the whole point of learning to make learning easy is to avoid computing the partition function every time because it's really complicated. So we are going to introduce a few approximations, which I hope you also remember as a general trick down the road if you deal with a tricky loss function. So the first one is this relaxation of it's a kind of a linear relaxation of an originally nonlinear function. So the log of z is upper bounded by its tangent, okay, and the tangent, the slope of the tangent, is a variable which is decided by the mu, and the touching point, okay, here happens when actually mu equals to this line, okay. So we can basically say that this particular function is upper bounded by this line, whose tangent is this value, okay. So with that, we replace this term with that, and we have this equation, which is now, let's see, it is nicer than that because now it is here a linear function of the coefficients we want to learn, okay, same as before, and in here it's no longer a log of the z theta of the theta, but a z of theta, which is still non-trivial, but at least we get rid of the logarithm sign. Okay, and here we only have a constant, okay, which is certain kind of value we choose to actually carry out this approximation. So we can take this, for example, as our. Of course, here you can plug in any value, but a reasonable value to estimate to plug here is the previous version of the estimation. Okay, so we put it as a theta t, and we call this implicitly theta t plus 1, but it's always a new value, so we ignore the index. All right, so we have something here, and but we need to still compute the gradient, right? Which is a little bit tricky if the argument is inside the z function. So we introduce some additional terms. For example, let's now make explicit the differences between the older version and the new version, and we bring them into this form. And now the log likelihood is written in this form. Okay. So what do we have? Okay. So we have this term, which is a linear term of my objective. We have this guy and this guy, which does not change. okay, with my estimation. We have this guy, which is the differences between the older and new version, and this guy is a function of theta as well, right? And therefore, when we take derivative of the whole thing, this guy will be taken derivative over. And we know that, exponent over a sum is a difficult thing to take a derivative over, because once you take a derivative, that exponent will still be there, and all you get is a multiplicative term outside of the equation, which is not changing the whole paradigm too much. So for that, we're going to introduce yet another approximation. We're going to now assume that the score of the feature subject to a convex combination, a convex constraint, bigger than 0, actually not convex, but a normalization constraint. They actually sum to 1, and each score is bigger than 0. That's a technical constraint you will find useful later on. And the more important thing is a Jensen's inequality type of relaxation, where you actually bring the summation from inside the exponential to outside of the exponential. Okay? And with that, now you have this nice property that this guy gets out of the equation, and the exponent is only operating on the score itself. Okay, so at the end of the day, you will have this equation. Okay. Actually, I'm wrong. The theta is still in exponent, but it's just by itself, and the weights are outside already. Okay, so without going through too much of the details, now you can take a derivative of the loss function with respect to each theta. Okay, and you will discover a update rule in which the exponent of the delta can be actually expressed in a closed form like this. Okay, and with some further write-up, you can now actually get an update rule where the delta actually can be computed in closed form from this particular equation. And that corresponds to an update of the full distribution as the original one multiplied by this particular form, which is a adjustment of the feature weights by the exponent of the delta in the weights. All right, and again, this derivation can be found in this equation, which I encourage you to examine after go home. But the true message, the most important message is that first, this delta theta can be now computed in closed form in here. And then there is a correspondence of the update function in the total distribution of the Markov random field. And here, actually, I want to draw you a connection between this law and this law. Remember our iterative proportional fitting, in which we are iteratively rescaling the magnitude of the clique potentials using this ratio of the empirical marginal versus the true marginal. And in here, what is happening is basically very similar. We are going to readjust the distribution, okay, by the ratio of the empirical weights of the score function versus the true expectation of the weights, okay, from your current estimation. And then they are lifted to the power of the feature score as indicated here. So there are kind of a correspondence between here and here. That's why this is called the generalized iterative scaling. It is more general, and it is still an iterative scaling algorithm, but the rescaling happens on this equation, which is a little bit more tricky to compute. All right? So to this point, I guess you guys had plenty of homework to do. It's kind of confusing in the equation. But in summary, I want you to take home the high-level ideas of these two algorithms. First, estimating parameters of a fully observed MRF can be complicated okay, due to the fact that inference has to be done. And in IPF, we have a fixed point equation, and our inference is to compute the marginal of clique using the true distribution in the current iteration. And in GIS, the inference is to compute this expectation over the feature function using the true distribution at the current version, and that's also very complicated. But once you know how to do that, you can use this equation to iteratively update the theta until convergence. All right, I think that's all for today. We have a few more slides to talk about the dependencies or the relationship between exponential distribution and the entropy function. That's for your fun and after class.